Today's lecture is going to be very exciting. We're going to see a very beautiful theorem called the Rahm theorem. And this theorem connects the two different ologies. It's going to connect cohomology with homology. Now, homology is more general. And you can do this for any topological space. Whereas cohomology is only for manifolds. You can generalize it to manifolds with boundary, and we also assume that the manifold is smooth. I did make a comment that it is possible to extend the theory of cohomology for topological spaces, but the way we're doing things, our theory of cohomology is just for manifolds. So it should not be a surprise that this one is probably going to be harder, and this one is easier. And we already saw an example of this. We proved the Jordan closed curve theorem. We tried to prove it originally using homology, and we ran into an obstacle. And the previous lecture, when we talked about cohomology, we saw that by taking advantage of cohomology, it was much more straightforward to prove the closed curve theorem. It was sort of the same method, but you approached it the cohomological way instead. And there's other ways in which cohomology may be simpler, and that's actually the theme of the entire book. And I mentioned this book before, but to say it again, it's called Differential Forms in Algebraic Topology by Bott and Tu. The theme of the book is they kind of do topology of manifolds, but they approach it through the point of view of differential forms, and they rely on cohomology to prove their results. The authors feel it's more elegant and it's easier to prove a lot of results than to stick to than rather to stick to homology. And I want to show you perhaps another example where cohomology, it's easier to get a result using cohomology instead. So let's say, that, so if X is an n-dimensional manifold and M is greater than n, then the mth homology group of X, your intuition will say it should be equal to 0. Because how many m-dimensional cycles do you have? None. Because the dimension of the cycle exceeds the dimension of the space itself. However, that's not a proof. If you think about it, what exactly is an M cycle? Well, it is an M chain with no boundary, with 0 boundary. But what is an M chain? Well, an M chain would be a formal sum of maps. So you would have a map from the m-dimensional simplex into your space. And the problem is, there's nothing wrong about this. You can easily imagine, like for example, if X is the circle, the one-dimensional circle, you can easily imagine maps from the two-dimensional simplex into the circle. You have lots. There's infinitely many of them. You have lots non-trivial such examples. And somehow you have to show that if you have an M cycle consisting of these, then you can find something of one higher dimension whose boundary will give you that chain. That is by no means obvious. Okay, so this result is true, but it does not follow directly from the definitions. Quite simply because you do not know anything about this map. This is a map in general. You really do not know anything about it. If you're interested, it is proven in Hatcher much later in the book. So he actually has to develop some extra machinery before he can come back and prove it. So it's true, but it's not easy to prove. However, if X is an is an n-dimensional manifold and m exceeds n, then it's a triviality, a complete triviality, to prove that the n-dimensional cohomology must be 0. Because cohomology is done using forms, differential forms. And when you rephrase this problem on the level of differential forms, it will be immediately obvious why it has to be 0. Because what is going on? Well, if omega is, and you can even forget about the fact that it's in the cohomology. You can just say any form of degree m, then such a form must necessarily be 0. So it's not just that the cohomology is 0, it's all of the all of the forms of degree m must be 0 forms. Well, technically you would say they do not have, maybe you would say they do not have 0 degree, but that's just a word game at that point. So why is that? Well, if it's an m form, then that would mean that by definition, omega is a coherent collection of Euclidean forms where each omega lambda is an m form. And since our manifold has dimension n, so we can say on E lambda, where E lambda is a Euclidean open set in Rn. So if you call the coordinates from x1 to xn, the coordinate functions on that open set, you get to see what the problem is. You have to choose m differentials. But because m is larger than n, you have to repeat them. Pigeonhole principle. You have to repeat them no matter what you do. And so at some point, you're going to come across a differential that will repeat twice. And the moment you get that, it's going to be 0. So that means in each of the charts, these forms locally in each of the charts, Euclidean charts, are 0 form. They're just 0. So that means the form globally is just a 0 form. That's why it means 0. It means that omega is the 0 form in each Euclidean chart. So a complete triviality, that just follows immediately by definition. So it does not require any clever argument. So I think this is nice. This kind of nicely shows how the cohomology approach is so much easier here to see why something is equal to 0. But what's the relationship? So this is really what the question is. What is the relationship? So the real question is, what is the relationship between the homology and cohomology? Of course, assuming that X is a manifold. So here's the theorem. And this is the Rahm theorem. Let X be a manifold. We do not care what dimension it has, but it's some manifold. Then the cohomology of X is isomorphic to, now you cannot say it's isomorphic to the homology of X. That's not going to make sense because this is a vector space and this is an abelian group. However, we talked about this functor called the dualizing functor. I'll remind you what it is in a moment, but really what you would put here is you would consider homomorphisms from this group into the reals, and the homomorphisms, they have the structure of a vector space. So sometimes this whole entire thing is denoted, so this is just equal to by definition. So sometimes we just write Hn of X dual. That's what we call it. We call it the dual of the group. So now this is going to be a vector space, a real vector space, and this is an isomorphism of vector spaces. So I have to remind you what this is. So recall, we have a functor And we call this functor Hamming on the right. We have a functor, and this is a functor from the category of abelian groups into the category of real vector spaces. So this is the functor. We can call it the dualizing functor. To briefly recall how this works, so if G1 and G2 are objects in a category of abelian groups, so in other words, they happen to be, so they're just abelian groups, then if you take Hamm of G1 into R, and you consider homomorphisms from G2 into R, then this will have the structure of a vector space. Over the reals, because if you have two homomorphisms, then the sum of those two homomorphisms is another homomorphism. And if you have a homomorphism, you can rescale a homomorphism by multiplying it by a real scalar. So the properties of a vector space will be satisfied. Another thing that I wanted to say, that if you have a group homomorphism, so in other words, you have a F is a morphism, so I'll write it as Hamm from G1 to G2. This might be a little bit confusing because there's two different Hamms. This is, maybe instead of calling it Hamm, maybe I should just call it MOR, a morphism. A morphism from G1 to G2, this is a morphism in the first category. Then you get the dual morphism, which now goes the other way. We just call it F dual. And F dual, so you put an upper star because it goes the other way. This is now a morphism from G2 dual to G1 dual. So you interchange the domain and the codomain. So we have a functor, sometimes we say a contravariant functor, and these get interchanged. Okay, so what do we do next? So the next thing that I wanted to say is, well, you have to check, of course, that this is a functor, but we talked about this before, right? We talked about this before. And one of the properties of the functor, and that we've mentioned, so this functor has the additional property that it preserves short exact sequences. So if you have a short exact sequence consisting of abelian groups, and you apply this dualizing functor, then you will have a short exact sequence of vector spaces. Now I should probably say how this functor is being defined, but it's the way, I did forget to put the duals right here. It's exactly what you think it does. So if you have an element, let's say alpha in here, then the way you get over there is you get it by composition. So it's alpha composed F. It's just a question of where you put the composition. So basically you're saying F star applied to alpha is alpha composed F. They get interchanged because it's a contravariant functor. And this should make sense because alpha is a map from G2 into the reals, and F is a map from G1 into G2. So when you do the composition, you get a homomorphism from G1 into the reals. So this is the dualizing functor. And it happens to preserve short exact sequences. And furthermore, and I did mention this, but we never even talked about this before. Furthermore, it also preserves exact sequences. So any exact sequence of any length, it preserves it. If you want to see the proof of this, so look at Wikipedia and look for something called an exact functor. And one of the conditions for being an exact functor, So there's like different ways of how you define an exact functor. So the way I like to define an exact functor is as a functor that preserves exact sequences, right? Because if you're calling it an exact functor, it should preserve exact sequences. But it happens to be the case, and it's a theorem in category theory, that if it preserves short exact sequences, then you can give a very nice argument by showing that it has to preserve exact sequences as well. In fact, maybe I can bring it up right now just to show it to you. So if you want to see a reference for this. So let's bring this up on Wikipedia and we get to see this. So as it says over here, so in homological algebra, an exact functor is a functor that preserves short exact sequences. So they define it to be something that preserves short exact sequences, but then they talk about what it means to be left exact, right exact, half exact. And there's I think it should be here somewhere. Looks like I cannot find it. Maybe it's under short exact sequences. Let's see. Yeah, so here it is. I think that's what it is. So there's a nice argument over here that requires you to decompose. If you have a sequence in general, so here's like an exact sequence: A1, A2, A3, A4, A5, A6. So this is an exact sequence. Let's say an exact sequence of abelian groups. If you have an exact sequence of abelian groups, the mapping from A1 to A2, it has a kernel. It has a kernel. So you go ahead and you write C1 for the kernel, but it also has a co-kernel, as you call it, a co-kernel. Co-kernel is just A2 mod the image of this map. So that would be the quotient. So that would be the co-kernel, as you call it. And then by putting the kernel and the co-kernel, you will end up getting a short exact sequence going like this. And then you kind of use the original sequence to create these diagonals with short exact sequences. And then if you know that the functor preserves short exact sequences, when you hit this diagram with the functor, you know all of these diagonals are exact. And you can use that information by chasing the diagram to then show that this horizontal one remains exact. It's a really cool argument. Like, it's really elegant. We call it an argument by abstract nonsense because we do not technically care what those objects represent anymore. So it's like an argument in the most general possible sense. So it's just something nice. So we did mention before that the dualizing functor preserves short exact sequences, but it's a very nice argument that it preserves short exact sequences. It actually has to preserve all exact sequences. Now, the other thing I want to say about the dualizing functor is we also know, and we talked about this before, that if you have two groups and you take their direct sum and you take the dualizing functor of that, you take their dual, then you're going to get something that's isomorphic to a direct sum of their duals. Likewise, if you take the integers and you take the dual of the integers, you're going to get the reals, something that's isomorphic to the reals. And finally, the other property that we mentioned is if you take a finite abelian group, Z mod NZ, then the dual of that would be isomorphic to the zero vector space, so the vector space that just consists of the zero vector. So these are properties of dual. And the de Rahm theorem says that if X is a manifold, then the n-dimensional cohomology can be calculated by taking the dual of the n-dimensional homology. However, you do have to be careful that you do lose information. So let me show you what I mean. Okay, so for example, if, let's say, the one-dimensional homology of X is isomorphic to Z plus Z mod 2. So for instance, the Klein bottle. So if you did that homework problem for calculating the first dimensional homology of the Klein bottle, this is what you get. Then the cohomology of the Klein bottle would be isomorphic. You would take the dual of this. And the dual of that would be isomorphic to the dual of the integers, direct sum the dual of this finite abelian group. But this dual would be R plus 0. And so what we see is the first dimensional cohomology of the Klein bottle is a one-dimensional vector space. That's what we see. So we are losing information that this extra factor kind of went away. So that's what we mean that if you know the homology, you automatically know the cohomology, but you cannot go the other way around. Just because you know the dimension, what dimension as a vector space the cohomology it has, you cannot recover this factor because the dual functor does not see it. But that's the illustration of the theorem. And now we're going to discuss the proof. So this is what we're going to do. So let me state the theorem again. If X is a manifold, then the n-dimensional cohomology of X is isomorphic to of the homology to R. Okay, and for simplicity, we just denote this by the dual. And now I'm going to give you proof outline. So here's what we're going to do. This is the big idea. This is the big idea that makes the whole thing work. And it's an amazing idea. This is the most interesting part of the proof. So you're going to be amazed when you see this. And the rest of the lecture will be dedicated to filling in some of the gaps of the outline. We're not going to be able to fill in every single little gap because there's too many gaps to fill in. But at least you will get the big idea of what is responsible behind the proof and how some of the ideas work. So we will give most of the proof, but we will have to leave a few things out. So for instance, one of the things that we're leaving out is the fact that the dualizing functor is an exact functor. Okay, I mean, it requires a check, but if we check every single little thing, this will be a 24-hour lecture. But maybe some people would like that. Okay, so let's think about what we're trying to do. So we're going to construct, we will construct a map from cohomology to the dual of the homology. So that's what we have to do. The name of this map will be called the Rahm map. You can also call it the Rahm isomorphism. So this is the map that's going to establish the isomorphism, right? We're showing they're isomorphic, so we have to construct the mapping. Now, let's say this. Now, usually, okay, maybe I should take this back. We will use the cubical version of homology. So what do we mean by the cubical version? In other words, you're going to define the n-dimensional chain in X. This is going to be a formal sum of smooth maps from the n-dimensional cube going into X. So this is what we call n-chains. Usually, when we deal with homology, we use the n-dimensional simplex, not the n-dimensional cube. But as you will see, we're going to be doing integrating. We're going to be doing some integrating. This is actually what makes the proof quite interesting. The proof relies on integration. So we're going to, therefore, calculate homology not by using continuous maps of the geometric n-simplex into X, but by using smooth maps of the n-dimensional cube. By assuming they're smooth, we're not actually losing any kind of information. That actually does require a proof, of course, and that's what we mean it's an outline. You could ask, how do you know that the two theories of homology are the same? And even if you're willing to buy that the cubical theory of homology is the same as the simplicial theory of homology, what happens if you add the assumption of smoothness instead of continuity? It will not matter. It will not matter for the simple reason because, I mean, this is, of course, not a rigorous argument, but the idea is if you have something that has like a lot of sharp corners, let's say, right, you have like a lot of sharp corners and it's not smooth, you can arbitrarily close it approximated by something that is smooth and it kind of stays arbitrarily close. So that means that if you have a continuous map, you can replace it by a smooth representative in the same homology class. That actually is a lot more analysis than it is topology, and it does require a proof. The technique which is used here, if you've ever seen it before, in analysis they call it convolution. So you take a certain convolution and you make it, you can smoothen things out. But like I said, outline. I'm trying to give you the big idea of how it works. So that's like the theme in math. Every theorem in math contains big ideas. The rest are details. But there's always that big idea that makes it work. And it's the most interesting part and the deepest part of the proof. So we have these. And then we have the boundary maps. And once you have the boundary maps, you can define homology. So, okay, so how do you go from here to here? So here's how you do it. The Rahm map. So given an element, an n form. So of course, in particular, what this means is because it's in the cohomology, it's in the kernel. So that would mean that its derivative would be 0. Okay? It also means that when we're writing omega, we of course are allowed to choose a different omega up to a representative. But we're just going to write omega. So choosing omega in here, we map omega. So we have to map it. Now this is the part which is a bit confusing. You're not mapping it into the homology. You're mapping it into the dual of the homology. So you have to map it into a homomorphism that takes you from here to there. So you technically have to map it. So you have to assign a homomorphism to omega. So how do you assign that homomorphism? So the way you do it is, so to assign a homomorphism, you have to pick something in here. You have to pick a chain. Technically, I mean, it's a chain, but it's a cycle, right? It has no boundary. So you're going to pick an n chain. So it's a formal sum of smooth maps with 0 boundary. And you have to assign to it a real number. So you pick a cycle. So a cycle is a special type of chain, n chain. And where do you map this cycle? You map that cycle to a real number. So you're going to assign it to a real number. And you're going to do it by integration. You're going to integrate omega over the cycle itself. That's the way you do it. This is the exciting part of the proof. So this is a form of degree n. This is a cycle of dimension n. The numbers are compatible, so you can integrate. Remember, we talked about integrating forms over chains. That's exactly what we're doing. And fortunately, this is a linear map because integration is a linear operation. That the integral of a sum is the sum of the integrals, right? That's just actually by definition. We define integration linearly on chains. And integration is also linear on forms. That if you have a sum of two forms, the integral of a sum of two forms, that's not hard to show, is then the integral is the sum of the integrals and all that stuff. So this is indeed giving you there. Now the question, of course, and this is the more serious question, checking that it's a linear map, that's the easy part. So this is the serious question. Is this map really well defined? That's the question that really matters. Because what if you choose a different representative? Right? What if you have a different representative? So let us show. So you have to show both ways. We need to show that this map is well defined on the level of forms and level of chains. Because there's really two issues where the map might become undefined. If we choose a different representative, maybe we get a different answer. But we're also choosing a representative in the homology. What if we use a different representative for a cycle? How do we know we get the same thing? So here's how it works. So let's first show that it is well defined on the level of form. So say that omega 1 and omega 2 are elements of the n-dimensional cohomology, and omega 1 is equivalent to omega 2. So what does that mean? It means that their difference, so if they're cohomologically equivalent, that means they're different. It's just like cycles. The difference of two cycles is the boundary of something of higher dimension. Here it goes the other way. Their difference would then be the derivative of something of smaller dimension. Let's call it eta, where eta is something in, well, maybe I should not say n plus 1. Maybe I should just say a form of degree n minus 1. By the way, if n is equal to 0, then, I mean, there's not much to check in that case. So this is what you have. And now then, the integral, so we have to check that these give you the same thing. Then what is c omega 1? That would be equal to, so we have to show the integral over omega 1 and the integral of omega 2 will give you the same thing. But what is omega 1? Omega 1 is equal to omega 2 plus d eta, right? We're just replacing omega 1 by, you're moving that over to the other side and you're just writing it like this. This is equal to the integral of omega 2 plus the integral of d eta. But that is, and this is the part that is really cool. You use Stokes' theorem. This is equal to, and this is Stokes' theorem. This is equal to the integral over omega 2 plus the integral of eta over the boundary of c. Right? Stokes' theorem. You can bring down the derivative downstairs, but then you have to take the boundary. But what do we know about c? C is a cycle. C is, in the homology, it's a cycle. So this is just 0. You're integrating over the empty chain. So this is just the integral over omega 2. Look at that, they're equal. So it is well defined. It is indeed well defined on forms. Why is it well defined on chains? So now let's say that we have C1 and C2, and these are two different representatives in the same cohomology, in the same homology class, and C1 is equivalent to C2 homologically. That would just mean that their difference is the boundary. This time, the degree is higher. It's the boundary of, let's say, C, where C is a chain of degree n plus 1. Then the integral of omega over C1. So now you have to show that if you integrate omega over C1 and you integrate omega over C2, regardless of what representative you pick, you end up getting the same thing. So this is going to be equal to omega, but C1 is equal to C2 plus the boundary of C. Now, because integration is linear on chains, that's the way it's defined, we have this. But then we use our favorite theorem again. We use Stokes' theorem. We use Stokes' theorem on the second integral. So that is d omega. And this time we get 0 for a different reason. Here we're getting 0 because it's a chain, but now we're getting 0 because omega is specifically chosen in the cohomology. So by definition, its derivative is 0. So this time the derivative is 0. And so we're getting that that's the same thing, omega C2. So there we go. So this map is well defined. So that's the big idea. Okay. So going back over here, what is the big idea? The big idea is quite simply that the Rahm map, this is what we call the Rahm map. The Rahm map is the map you get by integration. It's the integrating map. You're taking an n form that has 0 derivative, so it's in the cohomology, but you're taking an n form and you're mapping it to the dual of homology. So how do you map it? Well, so omega is being mapped. Maybe if you prefer it like this, you can basically say the Rahm map, it does this. Maybe we call this map D for Rahm. So let's call this D. No, let's not call it lowercase d. That looks funny. Let's call this DM. DRM. Rahm map. So how does it do it? So if omega is chosen in here, then DRM of omega is there. But if DRM of omega but if DRM of omega is in the dual, we have to say where DRM of omega, I have to say what it does to a chain. Right? If this is in the dual, I have to say what it does to a chain. And what does it do to a chain? It integrates. That's what it does. And that's the big idea, that this is indeed an isomorphism. It's an isomorphism, and from there, everything works out. So now we have to justify this. Okay? So like I said, it's an outline. That's what makes it work, Stokes' theorem. But now we have to actually justify that as an isomorphism. And that is what we're going to discuss next. Let us discuss how one would go about justifying that the Rahm map is indeed the isomorphism. So the idea here is that you take your manifold, so this is your manifold X, and so for simplicity, we're going to assume that X is compact. It does not have to be compact, but it's just going to make the argument easier. You can, of course, look in the Breton book, and he gives you a more general argument, but let's assume that X is compact. Then the idea would be that you can cover, so X is, you have pieces here, and this piece, and you have another piece. So this is a manifold. So because it's a manifold, there's a homeomorphism with Rn, and then there's another homeomorphism with Rn, like this, and so forth. So you basically cover your manifold by these charts. And all of these charts are homeomorphic to Rn, where n is the dimension of the manifold. Actually, maybe I should not call it Rn because we're using n for the cohomology, but something. Maybe call it Rm or whatever the dimension of the manifold is. So you you kind of cover it like this, and then you prove the idea is to show that the DRAM map is an isomorphism on small open sets. Then show that it is an isomorphism on the union as well. So that's basically how this works. So the first thing is, so we're first going to talk about why the DRAM map is an isomorphism locally, that if you pick a small enough open set on your manifold, why you have an isomorphism. And then we'll see what happens when you go to the union, when you take those open sets and you start taking unions of them. So let's begin with this. Now, the idea here is, because this is a manifold, it's locally going to be homeomorphic with Rn. So this is what I want to get to, and this is called the Poincare lemma. So the Poincare lemma says that if U is an open subset of Rn, and U is convex, then the DRAM map, so the DRAM map is the map from, this is the DRAM map. So from the, maybe we can call this M, from the n-dimensional cohomology of U to the Rahm, right, to the dual of the cohomology of U, that this is an isomorphism. The DRAM map is an isomorphism. So again, what's the DRAM map? The DRAM map says that if you were to pick an n-form on this open set, defined on that open set, so in other words, something with zero derivative because it's in the cohomology, you're going to assign to it the following element of this dual. This is the map that takes an n-chain and it assigns to it the integral, that we have an isomorphism. So basically, the DRAM theorem, this is basically what it says. The DRAM theorem, the DRAM map, and therefore the DRAM theorem is an isomorphism on convex Euclidean open sets. And we call this the Poincare lemma for obvious reasons, because it's used as a lemma in the DRAM theorem. I should say a little bit about the history. The DRAM theorem was conjectured by Poincare, and it was proven by de Rahm, by Georges de Rahm. And when you're proving this theorem, in the part of the proof of the theorem, it consists of various lemmas. So this is one of the lemmas that you use. This is now known as the Poincare lemma, which says that if you restrict everything to Euclidean open set, you see, when you're working with manifolds, you bring things back to Euclidean space, right? That's what manifolds are. They're locally Euclidean. So the Poincare lemma says that if you're working with convex Euclidean open sets, then this DRAM map, which you're investigating, will actually be an isomorphism. So the observation here comes down to this. Because U is convex, in particular, it is contractible. So that would mean that its n-dimensional homology would be 0 because it's contractible. The only degenerate case would happen when n is equal to 0, because in that case, this is connected, and so the n-dimensional homology would be Z, but the dual of Z would be R. And likewise, U is connected, path connected, so its zero-dimensional cohomology would also be R. So you have to treat the case when n is equal to 0 separately, but that's a lot easier. The more interesting case is when n is larger than 0, in which case the homology would be 0, right? Homology groups are 0, so the dual of those groups will be 0. And so to show that this is an isomorphism, you have to show that the cohomology is also 0. So basically, we need to show that the cohomology is also equal to 0. So they're both 0, and so the Rahm map is an isomorphism automatically because you're just mapping 0 to 0. There's only one such map, and that map is the isomorphism. So it just comes down to showing that this is therefore equal to 0. Now, what does that mean? It means, i.e., if omega is an n-form defined on U, and its derivative is 0, right? Because it's in the cohomology, its derivative is 0, then we can find a form of one lower dimension with its derivative being equal to omega, right? In other words, this form is the derivative of something that comes before it. That's what it means to be trivial in the cohomological sense, right? This is the omega is the trivial class. So everything in the cohomology is trivial. That's what that means. So that's basically what you have to show. So this is known as the Poincare lemma. So let us accept the Poincare lemma for now. Let us accept the Poincare lemma in order not to interrupt the flow of the argument. Because I'm kind of showing you the necessary steps you need to prove the Rahm theorem. So let's just accept this for now and move to the next thing. So remember what we said, Rahm theorem, the way you justify the isomorphism in the Rahm map, it comes down to two main ideas. You first do it on special open sets for which you know it is true, and then you pass to the union of those sets. Okay, so here is the next idea. So let's just remove this. So here's the next idea. Let's call this lemma. I'm not even sure how to call it. So here's the lemma. It says that if U and V are open sets, they're open subsets of some manifold X, and the D and the Rahm map is an isomorphism for U, V, and their intersection, assuming the intersection is not empty. If it's empty, there's nothing to check. Then it is also an isomorphism for their union. Now, what do we mean an isomorphism for U, V, and the intersection? It just means that you have to understand that because X is a manifold, and these are open subsets of a manifold, they themselves are manifolds. So Hn, so we have the following isomorphism. So this is the Rahm map. We have an isomorphism here. We have an isomorphism here. And we have an isomorphism on their intersection. Otherwise, it's just an empty set. So the empty topological space, which happens to be, if you like pathological, a lot of pathologies, then the empty space, that would be a manifold of every dimension. If you just think about that. But anyway, we have an isomorphism with this. Okay, so if these are isomorphisms, then on the union, you also have an isomorphism. That's what we're saying. So the whole point of this lemma is to take your manifold and break it into pieces. You're going to take a piece on which you know that Rahm's theorem is true. We're going to get back to that, but that's basically going to be the Poincare lemma on pieces you know for which it is true. And then you're going to choose another piece on which you know that the de Rahm theorem is true. And then if they intersect, and if you also know it's true on their intersection, you can just replace that, right? You can just go ahead and replace that by something larger, which is going to be their union. So you know it's true on their union. And then you take another one, if it's true on that one, and it's true on the intersection, and you keep on doing it. And if you happen to assume that X is compact, you do not have to, but it just makes it easier. So if you assume that X is compact, then you can obtain this by a finite process. And then you end up exhausting the whole thing, and you've established that you have an isomorphism on the union, but now the isomorphism on the entirety of X. That's the basic idea of like the steps that are being used to prove this. But let's discuss the proof of this lemma. This is actually a very interesting proof. This is going to be proof with almost, right, so some steps omitted. I'll have most of the steps there, but you have to carefully think through why some of the claims work. But the idea is going to start with this. We have the Meyer-Vitora sequence for homology and cohomology. So we have two sequences. So we have the one that goes like this. So for homology, you go from H n of U intersect V into H n of U plus H n of V. Then you go to the next one, H n of X. Then it goes down, H n minus 1, U intersect V, and like this. This would be H n plus 1 of X, like that. So this is an exact sequence for homology. But you also have, well, we also have an exact sequence for cohomology. This one will go a little bit differently. This one will go like this. It will go, let's say, H uppercase n of X. Then it will go H uppercase n of U plus H uppercase n of V. Maybe to briefly remind you that if omega, I guess instead of using X, I should use the union. Yeah, I'm working with the union here. So this would be U union V, U union V, because the union of U and V is not necessarily X. That's kind of what we want to eventually build up to, but it's not necessarily X yet. This would be U union V. The idea is if you take a form defined here, then you can restrict. You can do omega restricted to U, omega restricted to V, and then you get forms on that direct sum. But yeah, you go like this, and then you can restrict again to the intersection and subtract. So this would be H uppercase N of U intersect V. And then you go like this. But you see the next one, yeah, so this is going to be H n plus 1 of U union V. Like that. And then you will have the one that goes right before that, so that's H n minus 1 U intersect V. So the bottom one, that's cohomology. Now, you can see the arrows go in different directions. So you're going to apply the dualizing functor to the first one. So that will have the effect of flipping the arrows. So you will flip the arrows. You're using the Rahm functor. And then you dualize. And here we're using, so I'm saying some steps omitted. So one of the steps that is being omitted, so the Meyer-Vitora sequence for homology and cohomology, you're going to use the dual functor is exact. So it preserves exact sequences. So the sequence in homology that we just written down, it was an exact sequence, right? The Mayer-Vittori sequence is an exact sequence. And when you use the dual functor, you change the direction of the arrows, but the exactness of the sequence will remain the same. And that's what that is. Okay, so this is what we have. And we have the de Rahm maps. So the de Rahm map is the one that goes from cohomology to the dual of the homology. That's the de Rahm map. From homology to the dual of the, from cohomology to the dual of the homology. So you have all of these arrows that go like this. Now maybe the one on the direct sum should be explained a little bit, but basically you have a map from this factor to that factor using the de Rahm map, and you have a factor from here to here using the de Rahm map. So if you piece them together, you have a map from this factor to that factor. I'm sorry, from that sum to that sum. And because we're drawing a diagram on the board, you can guess that the diagram commutes. It can be shown that this diagram commutes. It has to commute. Otherwise, we would not even bother to write it down on the screen. So it's like I say this many times in class, that in a math book, anytime you have a diagram, it always commutes. But whenever you come up with your own diagram, it never commutes. So you get this deceptive idea that if you have some kind of diagram of objects, that it has to commute. But this one happens to commute. You have to verify this. You actually have to go through this. You have to pick, like for instance, you have this square over here. So you have to pick something in the cohomology class, use the de Rahm map. Well, you pick something over here, you map it over, and then show that the way it's compatible with the whole thing. So it takes an argument, but if we're willing to accept that the diagram commutes, so again, some steps omitted, but if we talk about every step, this will just go on and on. So we have this. And now we have something very interesting. We know we have an isomorphism. So consider the following part of this diagram. So this will be the part of the diagram we're interested in the de Rahm map on the union on the nth dimension. So the nth dimension on the union, we have a map, the de Rahm map, that goes to the dual. So this is the part that we care about. We want to show, right? Want to show this is an isomorphism. Because that's what we're claiming. We're claiming that if you have isomorphisms on U and V and on their intersection, then you have an isomorphism on their union. Okay, so this is, and then let's write down the relevant part of the sequence. So we have the union here. And as you can see, we have this one to the left, and then we have that one over here. So we have right over here, we have H, N, U intersect V. And here we have H, N of U plus H, N of V, like that. And then here, the one that goes after that one, well, the dimension will go up. So it's H, N plus 1, U intersect V. And then here we have H, N plus 1, U plus H, N plus 1 V. And we have the exact same thing with homology. So we have H, N star, U intersect V, H, N star of U plus H, N star of V. Now you have, of course, more arrows, but you do not care. This is the part of the sequence that you actually care about. Then you would have, what do we have here? We have H, N plus 1 star, U intersect V, H star, N plus 1 of U plus H star. Looks like I'm already confusing my stars with these. So this should be hn plus 1 star h. So we have this. I'm sure I probably messed something up, but it's the idea here that matters. And we have all, these are our Rahm maps. Now here's the thing. This one is an isomorphism, because we're assuming that this map, right, on U and V, we have isomorphism. This is an isomorphism. We're assuming we have an isomorphism on the intersection. This is the intersection. We have an isomorphism. So de Rahm's theorem is true on the isomorphism, and it's true in U and V as well. And we want to show that the one in the middle is an isomorphism. The map, it's a linear map because that's a map between vector spaces. The map in the middle is an isomorphism by using diagram chasing. It is not hard, but tedious. So maybe just to show you, let me just show you how this would work. Let's justify why this is an injective map, and then you can justify why it's a surjective map yourself. So basically, this is what you're going to do. You're going to pick something, let's just call it dot. You're going to pick something in here, and you're going to assume it gets mapped to 0. Okay? We're assuming it gets mapped to 0, and we want to show that this dot had to be 0 itself. That will, and that's what we need to do to justify that this is an injective map. And then you have to do something differently to show it's a surjective map. But we're just going to show why it's injective. So this goes to 0. Now, because this goes to 0, and this is a linear map, 0 goes to 0. So this goes to 0. 0 has to go to 0. We have an isomorphism over here. So the only element in this vector space that goes to the 0 vector is 0 itself. But now look at this. We have an element that gets mapped to 0. Well, if this element gets if this vector gets mapped to 0, it means it is in the kernel of this map. But this is an exact sequence. So that means there's something in here so it means this vector is in the image of there. So we can find something out here, right? We can find something over here that gets mapped to that one. Right? Now, this element gets mapped down here, right? This element gets mapped somewhere. Right? We have this mapping. So this gets mapped somewhere. And whatever that something is, by the commutative diagram, this goes to 0, right? This one is going to 0. Well, if it's going to 0, it means it's in the kernel. So because it's in the kernel, that means it's in the image. So there's something out there that goes to it. So there's something over here that goes to it, right? But look at this. This is an isomorphism. Because it's an isomorphism, there's something up here that gets mapped to it. Now, why does this complete the proof? Well, look at this. Therefore, we have proven that if something gets mapped to 0, then it is possible to go 2 steps back and find something in here that gets carried over there. But because this is an exact sequence, if you compose twice, you get 0, right? That this goes into the image, but the image goes to the kernel. So whatever that is, when you do it twice, it goes to 0. So that means pushing this over twice has to go to 0. So that has to be 0. So as you can see, to prove that this is injective, you have to go 2 steps back at some point. And to prove that it is surjective, somewhere in the argument, you would have to go out there. Okay, but I leave that up to you. You can try doing that. And this establishes that the map in the middle is an isomorphism. Okay, so that shows that it is an isomorphism. Okay, and now that we have this lemma, let's try. So now that we have 2 lemmas, we have the Poincare lemma, and we have this, maybe we can call this the gluing lemma or the union lemma. Let's call this the union lemma. And now that we have both of these lemmas, let us see how to put it together and try to attempt to make a proof out of this. Now we're going to come up with an attempt to prove de Rahm's theorem. We're going to assume that our manifold X is compact. It does not have to be, but this is to make it easier. And we can cover using finitely many open sets. So this is because of compactness. So that the de Rahm theorem is true for each ui. What's the justification here? Well, it's actually quite simple. Because when you have a manifold and you pick a point, the definition of the manifold is that locally you can find an open set that is homeomorphic to Rn. Okay? In fact, you could even say diffeomorphic to Rn, but it does not really matter here. Right? That's just a definition of a manifold, that locally it's Euclidean. Maybe I should not call it Rm. And because you have a homeomorphism, we know, so this is Poincaré lemma. This is convex. In fact, it's the whole thing, but in particular it's convex. So the Poincaré lemma applies. These two spaces are homeomorphic. De Rahm theorem is true over here, so it's going to be true over there. So the de Rahm theorem is true on each of those open sets. You want to somehow pass to the union, but you can only use two sets at the time. So the de Rahm theorem is true for U1 and U2. So if, now this is a big if, we do not necessarily know that, but if it is also true, so the de Rahm theorem is also true for the intersection, then it is true for the union. Now, what would be the problem with the intersection? Well, the problem with the intersection would be you have one open set, okay? So it is homeomorphic to Rm. And you have another open set. Now, they overlap. So let's say they overlap. So let's say this is U1 and U2. That's their intersection. So the issue here would be that if this intersection, you can either, it does not matter which of the two charts you use, because whichever one you use is going to have an issue. Like, you want to be able to say that they intersect. So let's say you draw the picture in the blue one. You want to be able to say that their overlap is convex. If you somehow knew that this was a convex subset of Rm, then this intersection is homeomorphic to a convex subset of Rm, for which the Poincaré lemma would say the de Rahm theorem is true, and that would be it. Now, it is conceivable that it does not have to be convex. They can it could be that the intersection is something like this. That's not convex. But they could say, well, maybe it's convex over here, right? Maybe this is convex, and then it's okay. Because then this one is homeomorphic to that, and that one is convex, and you can use Poincaré lemma. But the problem is maybe this one's not convex either. The issue is you do not really know how that intersection looks like in the charts. And that's a problem. But let's say we're willing to accept that. And then you just repeat. Then you would say the de Rahm theorem is true for the union of U1 and U2 and for U3. So if it is also true on their intersection. Now, what is their intersection? Their intersection by the distributive rule would be this. Okay, so this is true. So we're assuming it is true. We're assuming that they intersect in a way so the Rahm theorem is true. So this is true. This one is true. And when you intersect them, you get a triple intersection, right? You get a triple intersection. Okay, so we're assuming that as you keep on intersecting them, the Rahm theorem continues to be true, no matter how many times you intersect them. So then it would mean that the Rahm theorem is true on this intersection, and so by the lemma that we've just proven, so Rahm theorem is true on this union. And you just keep on doing this, and then you say it is true on the union of all of them. But the union on all of them is X. So you've proven that the Rahm theorem is true on a manifold X. But this is the problem. How do you know that you can choose sets in such a way? So so Breton gives a non-geometric proof, which is complicated. And you can look in how he does it. But there is a geometric proof. So this is what we have. We have a topological manifold. We have something better. So topological manifolds include something called smooth manifolds. And smooth manifolds include an even more special kind of manifold called the Riemannian manifold. So this is topology. Well, I guess you can say this is topology. Here you can say topology plus a little bit of calculus. And Riemannian manifold, this is geometry. Geometry with some calculus. This is what we call differential geometry. A Riemannian manifold, I would prefer to call it a geometric manifold. I understand that there would be somewhat of disrespect to Riemann, but geometric manifold makes the idea more clear. It's a manifold on which there is a notion of size. And it's not as simple as you think. Like you would think that maybe a Riemannian manifold or geometric manifold, it's a smooth manifold with a metric, like a metric space, but it's not that simple. Because when you're doing geometry, you're not just talking about the distance between 2 points. You also want to talk about angles and areas and all of that. So you need something else. So what exactly is a geometric manifold? So to maybe give you an idea, if I draw a sphere like this, and I draw a sphere like this, then you would say that these are the same manifold. There's a homeomorphism, there's also in fact a diffeomorphism, all that stuff. But not the same geometric manifold or Riemannian manifold. They have different sizes, they have different curvature, right? The curvature here and the curvature there are different. So here size begins to play a role. And if you're wondering what a Riemannian manifold is, I'll give you a very quick overview of what it is. So again, like I said, Breton avoids this discussion completely, but I think that we're coming close to the end of the semester and we're talking about manifolds. It probably makes a lot of sense to say what a geometric manifold is. So generally a smooth manifold is, you have a topological space, You have a smooth atlas. And then you have something else which we typically call a G. So what is G? G is a positive, definite symmetric tensor of rank 2. Now, you probably have no idea what that means. So I'll make it very simple for you. And this is the benefit of getting comfortable with differential forms. So this is basically like a differential form, except it is symmetric with degree 2, right? That's what I mean, rank 2, degree 2. So for instance, we would sometimes write a function, then we write like dx wedge dy plus another function dx wedge dz and things like that. But when we talk about positive definite, so when we talk about a symmetric tensor, we do not have the wedges. So we would write something like f dx dy plus f dx dz. And here you can write dz dx. It's treated to be as the same thing. And you can even have repetition. So you could have h dy dy twice. You can have repetition. What do we mean by positive definite? Well, you basically get a matrix out of these. So this is like dx, dy, dz, and so on. And then you dx, dy, dz, and so on. It's like a quadratic form, as you call it. So you want to have like, I mean, you basically, you just build a matrix consisting of all of these coefficient functions, and you're saying you want it to be a positive definite matrix. Why do you want it to be positive definite? Well, because in the end, you want to get something that plays a role of a tensor. I'm sorry, something that plays a role of a metric. You want something positive. And the way you can use this is basically if you have, so let's say this is your geometric manifold, and on that geometric manifold, you have, sometimes you call this a Riemannian metric, even though it's not metric in the normal sense, right, in the usual sense of what you think of a metric. But the idea would be that if you have, let's say, 2 points on the geometric manifold, and you have a path between them, so you have a smooth path. This is smooth. So we know what it means to be smooth because we have a smooth manifold. But now what you can do is you can calculate the length of that path. And the way you would do it is, and it's actually quite similar to how it works with differential forms. We first assume that this sits inside a single chart. We assume it sits inside a single chart. We map it. And then, because you have a mapping from the interval in here, you have this composition, and you can pull it. Okay, so normally we have a form, but here instead of a form, we have this we have this Riemannian metric. Now, I should say that this Riemannian metric is actually very similar to like a differential form. You define it in every chart. So in every chart, you have these local representations. So it's just like a 2 form, except you want it to be symmetric, and you want it to be positive definite, and you have the coherence condition like you have before. Okay, so it's very similar to what happens with differential forms. And then the way you would calculate this is you would kind of bring it back in here, okay? And when you bring it back in there, you're going to essentially end up with dt, right? And you'll have a function. Well, actually, to be fair, you will have dt squared. You will, because you're using 2 of them. You'll have dt squared, and you have some coefficient function in front. But to find the length, you use the Pythagorean theorem. It's the sum of squares. So you would then take the integral from 0 to 1 of the square root of whatever that is, dt. Okay, that's why you want it to be positive definite, because you want to make sure that the functions that you're getting are going to be positive, so you can integrate in all of that. So that's basically how this whole thing works. So it makes it possible for you to then talk about distances between 2 points. You cannot do that on a smooth manifold. You need this so-called, maybe you have this so-called Riemannian metric. It's not a metric in the usual sense. It's similar, but it's a bit different. And an idea that exists in Riemannian geometry is something called the geodesic. So a geodesic is basically a straight line on a geometric manifold. So for example, if we go to a torus, if you're here and you want to reach over here, the shortest distance between 2 points would go like that. And the analogy that people use is, if you were living, if the Earth was shaped like a donut, and you were living here and you want to get to it, by traveling in that path, it will feel to you as if you are traveling in a straight line. That's the way you will feel. You will feel that you're traveling in a straight line, even though when you look at it as an outsider standing over here, you can see you're not actually moving in a straight line. So it plays the role of a straight line. So in geometry, we talk about straight lines. But this is basically the analog of a straight line. Okay? And now the interesting thing that happens is geodesics may not necessarily exist, or they might be more than one. So if we go to the sphere, and I was to ask you, what's the geodesic from those 2 points? Well, you're going to travel along great circles, but there's actually infinitely many paths you can take. So we're used to the fact that between any 2 points in the plane, there's a unique line segment that connects them, and that happens to be the shortest distance between 2 points. But on a geometric manifold, like on a more complicated manifold, that's not necessarily true anymore. Or to use another example, consider this. Take the real plane and subtract away the origin. So the origin is missing. What would be the shortest distance between these 2 points? You want to say it's the straight line between them, but the problem is that's not part of your space. So you can go like this. But then you can make the path shorter, and you can make the path shorter, and you're kind of arbitrarily closing in on the straight line, but it's not part of your space, as you can see. Okay, so geodesics do not necessarily have to exist. And even if they do exist, there could be multiple such paths. It's just that the geometry of the flat plane happens to be quite nice. It happens to be very basic and simple, that you can get away with it. But in general, it's not going to work. But there is a fact that about so there's like a nice fact about geometric manifolds is that they locally have geodesics. So that would mean that if you give me a point on a geometric manifold, I can find an open set, and on that open set, you have a unique straight line between any 2 points, something that plays the role of a straight line. So we call these open sets, we call such open sets geodesically convex open sets. Because you see, they're playing the role of a convex set, that between any 2 points, there's a straight line, right? That's kind of what we're saying. That's what I mean by convexity, that between any 2 points, there's a straight line that connects them. So here, instead of a straight line, you're talking about geodesics. But other than that, it's going to be very simple. So here's how to complete the proof of the Rahm theorem using geometry. So I understand that maybe this is a bit bothersome because one has to use geometry, and that's something we've not really talked about. However, I think it makes sense to at least introduce the idea so you know what is out there in the world of manifolds. So people often talk about geometry, and this is going to be one of those instances where you introduce geometry. So the idea is basically this, that if X is compact, okay, maybe I should go back. Every smooth manifold can be given a Riemannian metric. Actually, this is not hard. I mean, one way to do it is you just have to give, I mean, this is like a very sloppy way, but basically you can give it a Riemannian metric in one chart, and then there's an overlapping chart. You use coherence to kind of put it together. It's just, when you go on and learn about Riemannian manifolds, you will see this. So you give it any Riemannian metric. It does not matter how. You just give it a Riemannian metric. And then from that point on, if we assume, so you then cover X using geodesically convex open sets. If we assume that X is compact, then we can use a finite number of them. So X is U1 union U2 union UN. But how do we know? So, oh yes, maybe I should take that back. Let me take it back. So if we assume X is locally homeomorphic to Rm, right? So right, it's a manifold, so this is locally homeomorphic to Rm. So here's what we say next. So let's say we have a point P, right? This is our point P, this is, let's say, the origin. It does not really matter where it is. Let's say it's the origin being mapped to that point, and this is homeomorphic. So here's the idea. We can find a geodesically convex open set containing P. Okay, so you can, if this red open set is not geodesically convex, well, I mean, we at least know you can find an open set homeomorphic to Rm. We at least know that. But because we have geometry, and there's a known fact in Riemannian geometry that you have these geodesics locally, so you can find like a smaller open set that is going to be geodesically convex. Now here's the whole point. This is convex on the Riemannian manifold. This will actually be convex in Euclidean space. The reason for this is because the idea is that this chart is locally describing the geometry around that point. So if for any two, because you want to think of geodesic as playing the role of a straight line. So if between any 2 points there's a geodesic, in other words, a path that minimizes distance, a unique path that minimizes distance, that is playing the role of a straight line. So when you convert it back to Euclidean space, whatever that path is, it's going to be a straight line here. So that's why this is convex. Okay, so thus every compact, does not have to be compact, but every compact manifold can be covered by a finite number of open sets which are geodesically convex. In particular, the Rahm theorem is satisfied on each of those open sets. Right? So we have the Rahm theorem, and it's true on each of these open sets. The reason for this is because each of these open sets, in the end, are going to be homeomorphic to a convex open subset of Euclidean space. So this is by the Poincare lemma. So where do you go from here? Well, here's the observation. Now, behold, these these convex sets will intersect in convex sets, will preserve convexity. That's the key point. That if you have something that's geodesically convex on the manifold, and you have something else that's geodesically convex on the manifold, then the intersection will be an open set that is convex. It's the exact same proof, because if you give me any 2 points in the intersection, those 2 points are both in the blue one and in the red one. And there's a unique path, minimizing path between them. So, I mean, it's a very simple proof that the intersection of convex sets is convex. So that would mean that if this is the Euclidean convex set that maps to it, it does not matter whether you use the blue one or the red one. It really does not matter. And this is how they intersect. Then the intersection will just be a smaller open convex subset of that. So it is still convex. And we can use the Poincare lemma on the intersection. So that is how it works. And I think this is an amazing proof because you're using geometry to work this through. That by introducing geometry, it just somehow very nicely works out. And because you know you can use the Poincare lemma on these intersections, and by the previous lemma that says that if it's true on the union and it's true on the intersections, if it's true on each individual set and it's true on their unions, then it's certainly true on the union of all of those open sets. And by putting all of that together, that's the outline of the proof of the Rahm theorem. I guess the last remaining thing that we have to address is why is the Poincare lemma true? And for that, I would just refer to you to Breton. I think he gives a very nice proof of that. I cannot really improve upon that. So you can just look at the way it's done in the book. And with that, I think that's enough of a discussion on Rahm's theorem. It's a very interesting theorem that connects homology and cohomology together.